All right, you can hear me okay? All right, thanks. This is an awesome workshop to the organizers, Tomer, Kevin, Eliza, others who did all this great work bringing this group together, and really feel privileged to go after the first few talks, which you'll see many resonant themes. So I'm going to be describing the work that a big team of us are doing as part of the DARPA Machine Common Sense program that Tomer mentioned, as well as a big moonshot mission project within the Center for Brains, Minds, Machines at MIT. You're going to hear from me and Vikash here, and then you'll also be hearing from several other team members, Kevin, Sherry, more from Tomer and Liz later on, but the work that we're going to be talking about represents the contributions of many individuals. As you've seen, especially in Tomer's and Alan's talks before, what we're getting at here is essentially AI's oldest dream. We ask, what would it take to build a machine that grows into intelligence the way a person does, that starts like a baby and learns like a child, and use that both as a way of scaling into something that's truly human-like forms of machine intelligence, but also to better understand the origins of our own machine, or our own intelligence. Now, this is, as Tomer said, this idea goes back at least to the founding of the discipline of computing, not just AI, as Turing famously articulated in his paper on computing and intelligence. And why do we think we can make progress on this now? Well, to put it simply, because there were things that we could only assume or presume back then about what a baby's brain and mind was like, which now we know much better. So in contrast to the idea that a children's mind might start off as roughly a blank slate with very simple kinds of mechanisms, we've learned a lot about the starting state, or the inductive bias, as well as the learning mechanisms. It's rather more structured, the starting state, than we thought. And the learning mechanisms, maybe some of them are much more sophisticated than we might have thought. So here I'm pointing to the work of some of the great developmental psychologists, both on our team and our collaborators and friends like Allison, who you'll also hear from later. And I think these are, in some sense, the most important people in the project are the developmental psychologists who for several decades have been unpacking these assumptions and showing us the empirical data. Stan referred to many of the same kind of work in the idea of sort of core knowledge here. So we're trying to understand from an engineering point of view, starting with, let's say, the idea of what you could call the common sense core, that from the very beginning, human thought is structured not in terms of just high-level patterns and pixels, like in a convolutional neural network, but in terms of objects and agents and their causal interactions, and systems of abstract concepts like intuitive physics and intuitive psychology that describe how these concepts work together. So the kinds of intuitive physics that you can see in this 1.5-year-old here, who's making complex plans, something like what Alan showed you in his symbolic planner, assembling a stack of cups, putting a stack of, having made a stack of 3, trying to assemble now a stack of 2, making goals and sub-goals and debugging those plans as bugs come up along the way. Or the kind of common sense psychology, for example, in the famous experiments with another group of 1.5-year-olds from Felix Warneken and Tomasello, where they showed famously that infants can see actions that they've never seen before and literally read somebody's mind, figure out what somebody's goal is and how to help them. So we're starting with trying to understand in computational terms, what is this knowledge that develops so early that's shared to some extent with many other species, but enriched and extended massively in humans, especially when language comes into the picture, but the common sense that provides the glue between perception, action, language, and reasoning. The big picture roadmap, that's just really the first stage, roughly 0 to 1.5 years, all the common sense that is built before language comes into the picture. But again, inspired by the rest of developmental psychology, what comes next, the stage of learning language on top of that core knowledge, and then using language and the new languages of thought that enables to learn everything else. Okay. But for now, we're starting on this first phase. And we want to identify here, and it's important to our approach, that there are certain hard problems of any common sense system that come up even in the stage of infancy. That's a very strong form of generalization. And problems that challenge, I think, the standard machine learning or reinforcement learning approaches. We need to be able to generalize to new tasks in really an infinite range, not an unconstrained range, but an infinite range of new tasks with essentially no retraining or fine-tuning, and also to vastly different kinds of environments that are very different from our training sets. So consider this 1-year-old stacking up cups where they invented their own task, right? The task now is to see, apparently, how many cups can I get on the back of a cat, okay? And they try that for a little while. When that proves to be a little bit difficult, they switch to a new task, which is basically can I get the cups to the other side of the cat, right? These tasks presumably were never demonstrated to this kid, and maybe had never been formulated by any human agent until he made them up. Or consider another young kid, about 20 months, who took what was a playground merry-go-round and decided to turn it into a obstacle course for his body. Or took one of his favorite toys on the playground, a shopping cart, and one of his favorite structures, the slide, and compositionally made up a new task, which is, can I get the shopping cart down the slide with my body? And he conceived of that task and executed it. Okay. So we want to understand what are the common sense systems that could achieve this kind of very flexible engagement with the world. Or consider, again, what I think is a challenge to any computer vision system, but certainly points to the aspects of common sense scene understanding that you can see even in infants, and classic infant cognition and perception experiments highlight this by placing infants, giving them visual stimuli that aren't like the ones they've seen in the real world, but showing that they can still deploy their common sense knowledge. Here, think about a scene that an infant probably won't make sense of, but any of us can, a basketball game. We can take an image like this, which is an image of a typical basketball game from a typical viewpoint, okay, and make sense of it, what the objects are, the agents, the goals, and so on. But that also applies to viewpoints like this one, which you might never have seen before unless you watched from a particular camera angle. You can still see the objects, the agents, the goals, the same stuff is happening. Or consider video games. This realistic video game where it's different at the pixel level, so it might confound, for example, a neural network that was trained on natural imagery and has some weird circles around the guy's body, but we have no trouble seeing it as the same thing. Or a less realistic video game where not only are the pixels less realistic, but somebody's doing a kind of slam dunk that nobody's ever done before, right? And you know that's unrealistic, and yet you can understand what it is and that it's unrealistic. Or consider other kinds of video games where the graphics are even worse, but the same common sense understanding is there. Basketball in Minecraft, no problem. Or even an old style Atari game, or even a really old style Atari game. This is from the Atari 2600 that I grew up on, right? Though it differs from the real world in so many ways, we see the people, the ball, we see the baskets and the goals. So ultimately, that's the kind of thing we're trying to build. But again, starting with the more basic versions of that you can see with infants. Now, again, here in this talk, I can only overview our high-level approach, and you'll hear more about this from Vikash and from our other team members later on in the day. But I think our most important key idea here is the idea of probabilistic programs and probabilistic programming languages, which I think can help us to implement in a unified way many of the ideas that both Alan and Stan were talking about in terms of languages for thinking, both core representations and the tools for building new languages of thought that go beyond that. Okay. You'll hear, Vikash is one of the world's experts in probabilistic programming, and you'll hear about the ways he's been leading the architecture of our team in this context in a little bit. Another idea is sort of more of a metaphor or a slogan, the game engine in your head. These are particular kinds of programs for building models of the world. They come from the game industry, software for modeling and simulating interactive 3D worlds. And it's an idea that we've been exploring for some time, that something like a game engine, something like it, might correspond to the kinds of core knowledge systems that could be built into not only human brains, but many others to start off with. Fast, approximate programs for simulating graphics, what the world looks like as you move through it, physics, navigation, the multi-agent plans or the plans of other agents, their goals, and simple kinds of planning. Okay. Now, we're not saying that Unity or something like that is built into your head. It remains wide open. What is the kind of mental game engine? But the key thing is that the game engine isn't just a training ground for some learning algorithm, but it's actually in your head. Right? And when I imagine making a plan, this kid here, that's Tomer's son, you've heard from him before, rolling the ball, thinking about will it knock over these blocks, something like a game physics engine might be a way for him to mentally simulate what would happen and to use that to guide his planning. Okay. So we've been building for a number of years in our group models of core intuitive physics and intuitive psychology. And here are just a couple of pointers to papers that have appeared in the last few years, which show some of our early attempts. And the exciting thing now is making a much more systematic and serious engineering effort using the kind of tools and conceptual framework that you'll hear about from Vikash. I just want to spend the last couple of minutes of my part just talking about learning, right? Because we do see that in a sense, tackling the common sense core or core knowledge, a lot of it is really more about trying to understand in engineering terms what evolution did, what is built in. But certainly human learning is the most compelling thing, I think, that brings all of us here, and the long-term roadmap requires that. So we can ask, what kind of a learning algorithm could build something like, for example, a physics engine, through some combination of evolution, biological, maybe cultural evolution, some of the kinds of geometry learning that Stan was talking about involve both biological and cultural evolution, and learning in an individual's lifetime, right? Essentially, if we're talking about a simulation program, we have to say, what are the program learning programs that could build this from the relevant different kinds of timescales of experience, okay? And from a developmental point of view, right, can we use the roadmap? This is just one small slice of the roadmap building on work from René Baillargeon and colleagues, but many others have mapped out at least rough kinds of milestones in the first years, especially the first year of life. Could we, for example, capture these different phases of knowledge of infant intuitive physics as different kinds of game engine representations, and then explain the trajectory of learning through some kind of program learning algorithm, which takes the kinds of experience that infants have and builds the kinds of increasingly accurate intuitive physics models that babies seem to do. Okay. Now, there are different approaches, again, that people in the field and in this workshop are taking. And even in our team, we also have been pursuing a mix or exploring the whole space of bottom-up and top-down approaches, right? So the bottom-up approach, which you'll hear more about from some of the other teams later on, is to start from almost from scratch with as little as you can and see if you can learn everything from infant-like experience and self-supervised learning algorithms. And a power of this is that you sort of only add in richer structure or learning algorithms when you need them, when they're demonstrably necessary to succeed on some learning task. Okay, that's powerful. But there are also drawbacks. You can underestimate how much is built in and how sophisticated learning has to be if the learning tasks aren't challenging enough. And we know that none of the learning tasks that we're working on in simulation right now are challenging enough. So that's a serious issue for us. And also, you don't initially use many of the insights from infant and comparative cognition research. In the top-down approach, you try to start with a minimal game engine, which is the intersection of what infant research and comparative cognition research suggests might be built in by evolution, and what we can effectively engineer, and then you try to learn the rest. So you learn in some kind of mental game engine. You learn to use the game engine for perception and planning. You use the game engine to ground language and then use language to learn everything else. Now, this also has drawbacks. We might be wrong about what's built in, and we might not know how to engineer key components that we think are built in. But we think on our team that we've made enough progress on both 1 and 2 that it's worth making a start on this and then learning from our mistakes as well as our successes. From a developmental psychology point of view, Tomer and I have a chapter that's in press in the annual review of developmental psychology, which talks about this research program and how it connects to the different stages of infant and early childhood cognition research. So we'll just point you to that, and I think it's just gone up on the Sci archive. So one version of this that Tomer's pursued is looking at, for example, learning in intuitive physics. These are experiments with adults, but we're working on analogs with younger children. How could you take simple, short scenes like this and infer, for example, the force laws, that some things seem to be attracting or repelling each other, or the other parameters like different masses or friction coefficients. And you can formulate this as inference in a hierarchical Bayesian model over structured program-like representations of the force laws. Okay? And here we're showing that model, at least roughly, corresponds with the judgments that adults make in this kind of experiment. Okay. But the bigger, harder problem, right, if you really want to learn something like a mental game engine, is you have to take seriously the fact that search in the space of programs is going to require dealing with a very, very complex, hard search problem, right? In contrast to what people find appealing about neural networks, where you have an end-to-end differentiable system that can be learned with gradient descent. There's no such nice geometry or topology in the space of programs. Yet somehow children solve this much harder search problem. So the idea that many of us are really interested in exploring is what you could call learning as programming, or the child as hacker, or the child as coder. There's a nice Trends in Cognitive Science article by Josh Rule, myself, and Steve Piantadosi coming out soon, which tries to articulate this view, called the child as hacker. That's the MIT version of hacking, is like doing awesome stuff with code, as opposed to the nefarious people who try to steal your credit card numbers and so on. But the key idea here, and I'll just point you to the paper, is just think about all the ways that in programming we try to make our code better, right? Things that go beyond just tuning parameters of existing functions, but writing new lines of code, or fixing a line of code, or writing whole new libraries of code, or even whole new languages, right? Or socially, culturally adapting code from other people. Our hypothesis here, and it's just a hypothesis, is that all these activities of coding have analogs in learning, and we need to build analogous learning algorithms. Now, how are we going to do that? This is still a big promissory note, or wide open, but it's exciting that there's a new discipline of what people are calling program synthesis meets machine learning, or learning programs, that involve combinations of some classic ideas of symbolic search with ideas of probabilistic inference and hierarchical models, like you've seen a minute ago, but also some powerful ways of using pattern recognition with neural networks. And I'll just point you to this community that's starting to emerge, such as the ICML IJCAI workshop 2018 on NumPy, or neural abstract machines and program induction, or a CogSci workshop that some of the same people that you see here participated in and organized. You might notice that this was on the idea of taking these methods, learning as program induction. You might notice the family resemblance, or actually the social cultural reuse of code in the workshop web pages. But these are just pointers to work that's starting to be done in a community that's starting to be built around the idea of taking inspiration from algorithms for writing code and bringing those into the study of human learning. So, what I've tried to do here is just to sketch out a roadmap and a toolkit, but it's really just the early stages. And I want to turn it over to Vikash to talk about some of the ways we're actually trying to build scalable engineering platforms and tools that will allow us to make this kind of roadmap and vision a reality.
Okay, so I'm just going to share a few words to try to give a sense of the flavor of the approach we're pursuing to implement some of these ideas. Really focusing on the engineering piece. How can we build a system which can go from the kind of perceptual input that a child might receive to symbolic game engine-like representations that support problem solving, planning, language understanding, ultimately, and other forms of thinking. And as Josh mentioned, achieving this requires integrating modes of modeling and inference from multiple eras of AI and cognitive science, including symbolic programs and causal models and hierarchical Bayes, deep learning, and simulation engines. Now, to actually engineer this, we've had to build some new programming tools, including the GEN probabilistic programming platform, which is available open source. And so I'll just share with you a couple of the components of our cognitive architecture that have been implemented in GEN, so you can get a flavor of what it would mean to actually integrate these different types of approaches into functional systems. So let's just start with the problem of the core common sense knowledge about 3D objects, that they persist in time and space, their motion is continuous, and they don't flicker in and out of existence. So these facets of, or these aspects of 3D objects have been studied in developmental psychology quite extensively, including by Liz Felke and many others. But state-of-the-art deep learning systems designed to detect objects don't work in accord with these principles. So this video is showing the flickering detections from state-of-the-art deep learning object detectors applied to a real-world object data set that we collected. And you can see that just moving the objects around, they disappear, the poses flicker, and the contact relationships are lost. So one of the first problems we set ourselves as part of this machine common sense effort was stabilizing these percepts by putting in symbolic prior knowledge about the structure of objects, their continuity, their persistence, and their contact relationships, writing probabilistic programs that draw on game engine ideas. And I'm showing a demo of that prototype system on the bottom, where we can see stable percepts of these two objects that remain stable with the object contact points highlighted in white, even while the deep learning object detections flicker on the top. So that's just sort of one small step using game engine ideas to try to create the foundations for common sense reasoning about objects. On top of that, we've been building in understanding of physics and the ability to explain anomalous events like teleportation or disappearance using game engine-like representations. And on top of that, we've been building the ability to model goal-directed behavior involving objects and places. So here's an example, similar in some ways to what Alan was talking about in his planning example, where we have a little probabilistic program that models the process of planning and replanning, where an agent navigates through an environment to accomplish goals, generating plans that are likely to achieve those goals. But because this is embedded in a probabilistic programming system, we can actually do goal inference. So we can take the same knowledge representation and perform online inferences about what goals an agent navigating the environment is probably trying to achieve. That is, we can run the planning engine forwards to make plans, but we can also perform inference working backwards from data to infer the probable goals that some other agent might have been trying to achieve. To do this, we had to combine planning engines with Monte Carlo inference to try to work out how each piece of evidence that accrues over the course of the agent performing its actions can be integrated to interpret to identify the probable goals of the agent. I just want, in closing, want to encourage people to take a look at some of the components that that are being used to develop these systems, especially Jen. I think just since we're out of time, I'll hand it back to Josh here. Thank you.
I wasn't planning any more other than that. I would just strongly encourage everyone to check out the new generation of probabilistic programming languages that Bakash's group is helping to build and others. And I think these tools will be important. It's really essential, not just for engineering common sense, but also for many other goals in computation that the cognitive science community could have.